V equals IR. This is Ohm's law. And what we learned last time was that if we have series resistors, we can get an equivalent resistance by just summing the individual resistors that are in the series. And for parallel resistors, it is sort of this reciprocal addition law. So we add the reciprocals of the resistors to get the reciprocal of the equivalent resistance. And hopefully you've had a chance to practice that a little bit. It just gives us more practice identifying series and parallel, which allows us to take a complicated circuit and simplify it. But today, we're going to learn a more generalized set of rules that allows us to kind of systematize this process. So right now, what we've learned, you're kind of winging it a little bit. You look at the picture and you say, okay, I think these are in series, so I'm going to combine them first. And there's no real order of operations. You just do it however you feel it. It's almost like an art form. And as the circuit gets more and more complicated, this becomes harder and harder to do. So we want to make it more systematic. And in order to do that, we're going to use, work done by someone else. These are known as Kirchhoff's laws. So these are the general principles that we can apply to any circuit. It doesn't really necessarily have to do with resistors in circuits, although it's applicable, but it could also apply to capacitors or combinations of resistors and capacitors. It also will apply to AC circuits. So it's a very general way of analyzing circuit. So the first rule, there's two of them, is called the junction or the node rule or law. And so basically, when we have a circuit, it's got all these branches. With stuff in there, right? It can have capacitors or resistors or whatever. So what is meant by a junction? A junction is any place where there's multiple paths in or out. So if we look where I'm drawing the red dots, these are all junctions. So they're basically all forks in the road. You've got one path going in and two paths coming out. So anytime, one wire connects to another wire and sort of gives an alternate option, that is a junction. And this rule or law says, it's very simple, that the current in to any junction has to be equal to the current out. That's the magnitude of the current in is equal to the magnitude of the current out. So this should be pretty sensible. I mean, if we have 1 amp of current that comes in from, let's just say we've got kind of a current I1 coming into this junction on the top, and then it splits into an I2 and an I3, then what the junction rule says is just that I1, which would be the current into that junction, is equal to the sum I2 plus I3. Okay, so that's just, that's basically kind of conservation of charge in a way, that there's nowhere the charge can't pile up at the junction, so it has to move through. If we get, a coulomb moving into the junction, then a coulomb has to also move out. And if it's a coulomb per second, 1 amp, then a coulomb per second has to be moving out. So it should be pretty, pretty straightforward. Then we have the loop law. And this one also is pretty straightforward. It says if we have any closed loop in a circuit, as we move around that closed loop from one point and return to our starting point, that we must have returned to the same potential we were at. So if you think about gravitational potential, just imagine you're in, a building with lots of floors. You start off in your office, at your desk on the 5th floor, and you get up and you go anywhere in the world and you return to your desk, that the change in gravitational potential energy must be 0. Okay, because you returned where you started. It doesn't matter how many floors up you went, how many floors down, what you did, whether you went out to the hot dog stand or what. You returned to your desk, so the net change in potential's 0. So to write this mathematically, we would just say the sum of the changes in voltage equals 0 for any closed loop. So in the little kind of mock circuit that I drew there's a lot of different closed loops. There's one that looks kind of like that. That would be a closed loop. There would be one closed loop that goes around the outside of this circuit. That would be a closed loop. We could have a closed loop that goes around this little loop on the right-hand side. That's a closed loop. I'll pick some different colors so it doesn't get too crowded. This would be a closed loop. And I mean, really anything, if you pick a point and you follow the lines and you return to that same point on any path you want, that would be a closed loop. So the loop law really gives us many, many equations for a complicated circuit. The junction law also gives us a whole bunch of equations. So for this particular circuit, I would be able to get 4 equations that would be junction law equations. And in terms of loops, that's hard to count, but let's see, let me think for a minute. There's 1, there's 2, there's 3, there's 4, there's 5, there's 6, there's, I don't know, there's like 6 or 7 at least loops that I can see. So we're gonna start with a little bit simpler circuits and practice this, and then we'll move into more complicated circuits. So what happens when we generate these equations is we wind up with a system of linear equations for the currents that will allow us to solve for the current in every section of the circuit. So that's basically the same thing we were doing with, using series and parallel, but it's much more systematic because we don't actually have to combine them. And then once we combine them, we find the current going into the equivalent resistor and then sort of unfold our final circuit and open it up and look at, each step along the way. Additionally, there are times when we don't really have series or parallel. So what do you do then? Well, Kirchhoff's laws don't really care about series or parallel. So let's just use it to try for a simple circuit and see how we could use these. Okay, so there's a very simple circuit, and suppose the voltage is 12 volts, and R1 equals 1 ohm, R2 equals 2 ohms, and R3 equals 3 ohms, just to make it easy to remember. And we want to find the current through each one. So the first thing we need to do is we need to draw our circuit and then label currents. We have to imagine currents flowing around. So we've got some current coming out of the battery. We can call that just I. And then it splits into, well, let's call it an IA. And then it splits into IB and IC. Now, sometimes I call these I1, I2, I3, but I don't want us to get confused by thinking that I2 has to be only the current going through resistor 2 or something like that. Okay, because we have the same current going through resistor 1 and resistor 2. And so just to avoid confusion with the labels. So let's see what equations we can write. First of all, how many junctions do you see in this circuit? How many junctions or nodes?
Two.
Yeah, there's two. Where are they? They are here and here. Let's call them junction 1 and junction 2. So from junction 1, we get an equation. The current into junction 1 is IA, and the current out would be the sum of IB and IC. For junction 2, well, if we follow these red lines, what's coming into junction 2 is IC plus IB. And what's coming out of it, well, we didn't label that. Okay, we didn't label that. Why didn't I label it? Because it's actually the same as IA, but just for the sake of argument, what if we didn't know it was the same? We might have called it ID. So if we label things that way, then what we get from the first two junction rules says that IA equals the sum of IB and IC, and the sum of IB and IC equals ID. And so these guys together would tell me that IA equals ID. So, generally, if we don't have a junction between 2 points, then the current has to be the same everywhere between those 2 points. So from junction 2, as I move around through my battery up to junction 1, there's no other junction. So whatever is the current in any part of this branch, this whole left-hand side, it just has to be the same current. And going forward, I wouldn't label those separately. I would just call them both IA. But that ultimately comes out of the junction law. So generally, like I said, if I just called this IA, then look what would happen. My junction laws would become redundant. They would basically say the same thing. And that's pretty common with the junction law. We get more of them than we can use. So they are not always linearly independent equations. If you're rusty on your math, you may not really know why that's important, that we have independent equations. When we're solving, let's say, 3 equations with 3 unknowns, it's not enough to have 3 equations. With those 3 unknowns, those equations have to be linearly independent, which basically means, we cannot get one of them by combining the other 2. So they're really independent. Graphically, with 2 equations and 2 unknowns, it would mean that those lines are not the same line. With same thing, 3 equations with 3 unknowns, you'd have lines in 3-dimensional space, and you can't have one line being a multiple of another line, but you also can't have it such that 2 lines form a plane and the third line is in the same plane as the first 2. Okay, so at any rate, it's not enough. We don't have as many equations with the junctions as we think we do, because they tend to overlap and give us the same information. So we will always need to go to loop equations. Okay, so how many loops do I have? I see 3 loops. So the loops that I see are one that goes around like that. Let's call that loop 1. And then I see another loop that goes around over here. We could call that loop 2. And then there's one big loop that goes around the outside. We could call that loop 3. So I'm hoping you guys can see color, because I'm using the color here to differentiate between my loops and my junctions. But if you're not really good with color, then maybe you can put 1L, 2L, 3L, and 1J and 2J or something like that to differentiate them. Okay, so then we're going to write down a loop law. So there are some rules for how to figure out the signs of these things. But let's start without worrying about signs, and let's just imagine we're on loop 1. And so we start at the beginning of my loop and we start walking. And we're just going to write down everything we see as we walk. So the first thing we see is the voltage of the battery. Okay, I see a voltage. So remember, think of voltages like hills. And so the first thing we see, we started below the battery. So we kind of go, we hit this battery, and it's like the machine, the conveyor belt that brings us up to the top of the roller coaster. So there's a hill there. And then we walk along and we don't see anything else that changes voltage until we get to this resistor. So there's a resistor I1, and so the voltage across that resistor would be the current, which is IB, times the resistance R1. Then we keep walking and we get to resistor R2. So the current through that is also IB, so the voltage is IB times R2. And then we keep walking, and eventually we get back to our starting point. So once we get to our starting point, we know that we have gotten back to 0. And all I have to do really is know how to fill in the signs. Okay, so to fill in the signs, I have to know as I go across each element that has a voltage, whether I'm going uphill or downhill. So let's take the battery to start with. The long side is the positive terminal of the battery. The short side is the negative terminal. So what's happening is we're coming up to the battery and we're approaching the negative terminal. And then when we leave the battery, we're at the positive terminal, which means we have moved uphill. Okay, we went from the bottom of the battery, the negative terminal, to the top. So we went uphill. So we're going to get a plus sign for that voltage. So the sign of the voltage is an interplay between what my battery, how it's oriented, and the direction that I drew my loop. So I drew my loop going clockwise. So as I cross the battery, I'm going from the negative to the positive, so I'm going uphill. Had I drawn my loop going counterclockwise, I would have first hit the top of the battery, and then I would have gone to the bottom. So I would have gone downhill as I went across the battery, and I would have a minus sign. Okay, so the signs are always an interplay between the directions of, the circuit elements and the current, and the direction of how I drew the loop. And it does not matter how we draw the loop. We don't care how we draw it. We don't put any thought into it. Just once we've drawn it, we have to be careful when we're coming up with signs. Then I come to resistor R1. And I have to know, am I going uphill or downhill as I go across that resistor? Now, there's really only one thing that determines this. Keep in mind, this is a simple circuit, and we know kind of what's happening. We know we go up on the battery, and then we go downhill as we go across R1 and R2 because it's a simple circuit. But in a complicated circuit, we may not know just looking at it if we're going up or downhill. And even maybe we don't know that for a simple circuit yet because we don't have that much experience. Here's the only thing we need to know. We need to look at the current, and the current flows downhill, right? You go to any river in the world and you look at which way the current is going. And if you follow it, the direction the current's going, you're going to move downhill. Okay, you're going to move downhill. Eventually, you're going to get to a lake or the ocean or something, right? But water current always flows downhill, and electrical current also always flows downhill. So when I come to resistor R1, all I have to do is look at the current. And if I'm going with the current, then I'm going downhill. Are we going with the current as we go across R1? You have to imagine we're kind of walking along this blue line, and we get to R1, and we're walking, the direction of the blue line is the same as the direction of the current. So we are walking with the current as we cross R1, and therefore it gets a minus sign because that resistor is a downhill resistor. Okay, it's downhill the way we're walking. Same goes for R2. The current through R2 is pointing down. My blue loop is pointing down as I cross R2. So I'm going with the current, which means I'm going downhill to lower potential. Current always goes to lower potential. Okay, so that's it. Right now, we only have two circuit elements to worry about, the battery and the resistor. So for the battery, we have to think, are we going from the negative to the positive, which would mean we're going uphill? Or are we going from the positive down to the negative, which means we're going downhill? For the resistor, I have to know whether the loop direction that I drew is the same as the current direction that I drew. Doesn't matter if I drew the current correctly or not, by the way. Doesn't matter. It's just, is my loop direction the same as the direction that I drew the current? And if it is, then I'm going downhill and I get a minus sign. If it's not, I'm going uphill and I get a plus sign. Okay, then let's do loop 2. So we look at where I started. I started drawing the loop between R1 and R2. So the first thing I'm going to hit is IB times R1. That's the first element that has a voltage, and I have to write down the voltage across that thing. Again, I'm not worrying about the signs yet. I'm just listing everything that we encounter on our path. Then we walk around. The next thing we see is R3. So we're going to have an IC times R3 because the current going through R3 is what we call IC. Then we keep going. We finally come to R2. The current through R2 is called IB, so we have IB times R2. So it's Ohm's law for all three, telling us what the voltage is across each resistor. And now we need to go in and fill in the signs. So when I go across R1, am I going with the current or against it? Going like this. Going, did you say against it?
Yes.
Yeah, I'm going against it because IB goes down, but my loop direction is going up at that point. So since I'm going against the current, if you get in the water, the river, and you start walking against the current, it's hard to go against the current. You're going uphill when you go against the current, so you get a plus sign. Then we get to R3. Are we going with the current or against it? We're going with it, right? So if we're going with it, we put a minus sign. Then we come around to R2, and again, on R2, we are now going against the current, so we get a plus sign. All right, so I have now 3 independent equations. So with the junction laws, I really only get one equation. And now I have 2 more independent equations. At least I hope they're independent. It's possible if I try to solve them, I find out that they're dependent, and I didn't predict that. But in principle, I should be able to solve this now because I have enough equations. However, for practice, we should go ahead and draw loop 3, the equation for loop 3. So what I'd like is for you to try to draw the equation, write down the equation for loop 3 on your own, filling in the signs, and then in a couple of minutes I'll do it. And that way you can test your thinking and make sure you're understanding the signs. If you are watching the video later on, you should still be sort of during this time working this out. You should be pretending you're watching it live. You guys anyone ever get a voicemail from someone that was so long that you forget it's a voicemail and you start nodding your head or you say uh-huh or something to the voicemail? You ever done that? So when you're watching the lecture, it should be like that. I want you to like go uh-huh. You know, forget that you're not live, for those of you who are not live, and just, you know, treat it like it's a regular lecture. Talk to the screen, you know, ask questions. And when you feel like you want to ask a question, you can send those to me in email. Okay, let's see. What do I get for this? So I'm starting above my battery. So I don't see anything until I get to R3. So I have an I, C, R3, and then we keep going, and then I kind of get to my battery. You may have put the battery first, which is fine, because I was a little bit ambiguous in like where does this thing go? It has to go, you know, right to the starting point. Then we figure out the signs. So for the ICR3, we're going with the current, so we get a minus sign. And for the voltage, I'm going from the negative side to the positive side. So I'm going uphill as I go across that voltage. So is that what you guys got? Minus IC R3 and a plus V, maybe not in that order. Okay, good. So now we have 3 equations with 3 unknowns. So we want to solve it. How do you solve 3 equations with 3 unknowns?
Substitution.
Yeah, we generally use substitution. Now, if you have only 2 equations with 2 unknowns, it's really easy. And of course, you can use elimination, but I know students like substitution better. And, you know, either one works. But once you get to 3 equations with 3 unknowns, you could wind up going in circles. Okay, you could wind up going in circles. Anyone ever had that experience? Like you're substituting and then, you know, like at some point you've done like 6 or 7 substitutions and then the equation you get is the one you started with. And you're, oh, you know, can't believe I did that. So I'm going to tell you how to avoid that. Okay, these equations, this is, hopefully you don't have a lot of experience with this, but this is my analogy. This will tell you something about the apartments in my college town, but this is like if you have roaches in your apartment and you want to get rid of the roaches, okay? And it's not good enough to just go turn on the light and watch them scatter, okay? You have to really get rid of them. So suppose you put some poison out in a room to get rid of the roaches. If you do that, the roaches are going to leave that room, but they're just going to go into another room, okay? And if you a month later, you decide, okay, I'm going to put poison in that other room, they're just going to go back into the first room, okay? And that's what happens with variables when you're trying to eliminate them. It's not, you have to put the poison in the whole building, okay? It's not, if you have an apartment and you have someone spray your apartment and you get rid of roaches in your apartment, they're just going to go into the neighbor's apartment. And then in a couple months, they're going to come back into your apartment. So you have to get rid of them from the whole building. So when you want to do a substitution, let's say we decide, hey, I'm going to get rid of IA. So I know that IA equals IB plus IC. So what you have to do is you have to go through all of your other equations and get rid of IA. Okay? You have to get rid of it from all of your equations. Now this is a pretty easy one, so it's, you know, it's not, we're not going to wind up stuck in a circle. But for other you know, situations, other systems with maybe 5 loops or 7 loops and, you know, 5 currents, then you are really asking for trouble if once you take an unknown, once you take one of your variables and substitute for it, you don't do that in all of the equations. Okay, now this one, this is sufficiently easy that I don't think we're going to have trouble, but we will see some where it gets harder, and then that's important to keep in mind. So if I'm going to solve this, so I'm probably going to look at my loop 3, because it's really easy. It only has one unknown. So if I take loop 3, and I rearrange it, I get V equals IC R3, and so IC is just equal to V over R3, which is, 12 over 3. That's going to be 4 amps. So I can solve directly for one of them, and then it's almost like dominoes. If I look back at equation 2, I see there are only 2 unknowns, and those unknowns are IB and IC. Keep in mind, we know all of the resistances, right? So we know R2 and R3 and R1. We know all of those. So the only unknowns are IB and IC, and so we could just go into that equation. And if I want to go into that equation, I want to get the IB stuff by itself. So I would rearrange and have IB R1 plus IB R2 equals IC R3, and we can factor out the IB. And so IB is going to be equal to IC R3 over R1 plus R2. And that is 4 times 3 over 1 plus 2. That winds up being also 4 amps. So we know the current IC and we know the current IB, and if our task is to find all of the currents, we would then have an IA, which is, and this is using loop rule 1, IA is equal to just IB plus IC, which is going to be 8 amps. Notice we never had to do something like, say, R1 and R2 are in series, and then once we combine them in series to say that thing is in parallel with R3, and then combine those in parallel and get any equivalent resistance. In fact, if I want to know the equivalent resistance of the circuit, I could solve this way and then say just V equals IA times R equivalent. And that would be, 12 equals 8 R equivalent, and R equivalent would be then, 1.5 ohms. If I wanted to know it without actually using series and parallel, I could solve the whole circuit, and then whatever's coming out of this battery is going into some equivalent resistor. So there's 8 amps coming out of the battery going into an equivalent resistor, and the voltage is 12 volts. So that would be an alternative approach. Is this easier than using series and parallel? I wouldn't say so. I would say it's different. It's maybe the same amount of work, but there's less art to it. You just kind of get your equations and then solve them. Whereas the combinations of series and parallel, you have to kind of have an idea of a path to follow, what you're going to combine first and what you combine next, and so on. Okay. So we have an R1, an R2, and an R3, and a V1, a V2, and a V3. V1 is equal to 8 volts. V2 is equal to 16 volts. And V3 is equal to 4 volts. While R1 is 10 ohms, R2 is 20 ohms, and R3 is 30 ohms. So geometrically, this is pretty similar. So we are going to have the same number of loops, same number of junctions. We can label our currents IA, IB, and IC again. And then our junction laws will say IA equals IB plus IC. And we could call that junction 1 again. Now, our experience tells us that junction 2, the second junction, is going to tell us the same stuff. Okay? That is, it's going to be IB and IC going in and IA going out, but it's going to give me the same equation. So then we'll move to our loops. So, I mean, you can draw them any way you want. It doesn't really matter how you draw them. I'll just draw them all going clockwise. Just like we did before. But you can draw them counterclockwise, you can mix and match, it doesn't matter. So loop 1, I'm going to go a little faster at it this time. We're going across our battery, so we have a voltage V1, and it's a plus because we're going from the small side, the negative side, to the positive side. We're going uphill as we go across that battery. Then we get to R1, and we're going with the current, so we have a minus sign, minus IA R1. And then we get to R2, we are again going with the current, so it's minus IB R2. And then we get to battery V2, there is a voltage V2, but now we're starting at the top of the battery and we're going down to the bottom. So we get a minus sign there because we're kind of going against the battery. We're going the wrong way. And that's it. We get to the bottom. So then for loop 2, the first thing we see is V2. And now we're going with the battery. We're going in the direction the battery is facing. So we have a plus sign. You don't have to write the plus sign there, but I'm writing it just to remind us all that we thought about it already. Then we hit resistor R2. So we have an IB R2, and we are going against the current. So we get a plus sign there. And now we come to IC and going through R3. And we get a minus sign because we are going with the current. As we pass through resistor R3, we are following the direction of current IC. And we come up to the battery V3, and we are lined up in the same direction as the battery. So we're going from minus to positive. So we get a plus sign. We're going the way the battery wants to push the current. That adds up to 0. Okay, and our last loop, we start above the battery V1, so I'm not including that yet. I hit IA R1. I get a minus sign because I'm going with the current. Then we get to IC R3, again, a minus sign because we are going with the current. Then we get to battery V3. It's a plus V3, just like last time, because we are moving across the battery from the bottom to the top of the battery. And then we get to V1, it also gets a plus sign because we're moving from the bottom to the top. Okay, so if we want to solve these, I kind of picked easy numbers to make this a little bit easier for us to solve by using the numbers. We have a system of equations. We can solve it exactly symbolically, but it's probably not worth the time because realistically, if we're solving these for a complicated circuit, once we have more than 3 equations and 3 unknowns, we really just want to make a matrix out of it and solve it by inverting the matrix. So maybe you've learned how to do that in math class, maybe you haven't, but you will learn that for sure in linear algebra, but maybe also in a circuits class you might do it that way. It's basically you're letting the computer solve the system for you in a systematic way. So let's go ahead and put in our numbers for the voltages and for the resistors, and kind of make these equations look simpler so we can look at how to attack them. So V1 minus V2 would be, there's an 8 minus a 16, which gives me a negative 8. And then we have minus 10 IA and minus 20 IB equals 0. So the first equation becomes negative 8 minus 10 IA minus 20 IB equals 0. Now the fact that these all have minus signs indicates that at least one of our currents is going to be negative, which means that the way we drew the current in the diagram is wrong. Okay, the way we drew the current in the diagram is wrong for at least one of those currents. But that's okay. It doesn't matter at all. When we get answers at the end of the day, if we find out that IA is, let's say, minus 1 amp, that would just mean it's 1 amp going the opposite direction to how we drew it. And we're still done. Okay, there's no more work to do at that stage. For the second equation, we have a V2 plus a V3. So that's a 16 plus 4 or 20 plus R2, which is 20 times IB, and then minus 30 times IC. And then for equation 3, we have a V3 plus a V1. That is a 4 plus an 8, or 12, minus 10 IA and minus 30 IC. Okay. So let's kind of think about this a little bit before we try to solve. Because if I'm not careful, we can get in that circular loop. So what I want to do is I want to pick one variable and I want to get rid of it from all of my equations. So we could decide to eliminate IA from everything. We could decide to eliminate IB from everything, or IC from everything. Doesn't really matter. I'm looking at my equations. I see that my third equation has IA and IC only. So could I combine the first 2 loop equations to eliminate IB, because IB is already missing from equation number 3. And when I look at it, I see, yeah, actually it would be very easy to eliminate IB from the first 2 equations. All I have to do is add those 2 equations. So again, those equations are called equation 1, equation 2, and equation 3. So we can make an equation 4, which is just equal to the sum of equations 1 and 2. If I add equations 1 and 2, what am I going to get? When I add them, the negative 8 plus the 20 gives me a 12. And the IBs cancel, And then we have minus 10 IA minus 30 IC. And look what happens. This is equal to equation 3. That's no good, okay, because those equations are not linear. Sorry, they're linear. They're not linearly independent. That's what I meant to say. What this tells us is we can't get away with just using the loop equations, okay, because these 3 equations are not independent. And that is in general going to be true. We're going to have to use a combination of junction laws and loop laws. Okay, that is always going to be true. Otherwise, there wouldn't be a junction law because there's always lots of loop equations and there's more loop equations than we need. But we need the junction equations as well. So let's take a different strategy. Let's try to eliminate IA by using equation 1 for the junctions. Okay, if we do that, we would take equation 1 and substitute it, the red equation 1, into the blue equation 1 to eliminate IA. So what do we get? We get minus 8 minus 10 times the quantity IB plus IC minus 20 IB equals 0. And then we're going to take equation 1 from the junctions and insert it into equation 3. That one gives me 12 minus 10 times the quantity IB plus IC minus 30 IC equals 0. Let's simplify. This gives me minus 8 minus 30 IB minus 10 IC equals 0 for the first equation, and 12 minus 10 IB minus 40 IC equals 0 for the second equation. So that really looks like 2 independent equations. How do I know they're independent? Because they're not multiples of one another. If I multiply the second equation by 3 to get a 30 IB, the IC becomes a negative 120 IC. That will not match the IC term in the previous equation. So these are really independent, and we can try to solve them. Okay, let's call these guys equation 5 and equation 6 respectively, because I already tried to call, and I'm not going to color them with a particular color here, 5 and 6. I already made an equation 4 that didn't work out. Okay, so I don't want to reuse that label. So how can I solve these? Well, we can use substitution or elimination. I would probably lean toward elimination. That is, I would take equation 5 minus 3 times equation 6. So can you see why I would want to do that? Yeah, so Ben, why do I want to do that?
Because you'd be able to eliminate the IB then.
Yeah, exactly. So I would recommend actually writing them over: minus 8, minus 30 IB, minus 10 IC equals 0. And then a -3 times 12 is -36. A -3 times -10 is a +30 IB. And a -3 times -40 gives me a +120 IC. Then when I add them, you can see that the IB term disappears. And we get a -44 plus 110 IC equals 0. So IC is equal to 44 over 110, which is, it's not really worth keeping these fractions around because it gets very hard to get common denominators between all of them in general, okay, unless we picked really nice numbers. So that's 0.4 amps for IC. Now, once we know IC, we can go back into these two equations and find IB. So maybe we take equation 5 and, rearrange it. We're going to have -8 minus 30 IB minus 10 times 0.4 equals 0. So I'm putting in my IC as 0.4. That's a -8 minus a 4. I get -30 IB equals 12. And IB equals 12 over -30. Which is -0.4. Okay, and then finally we want to find IA, which is IB plus IC. That is -0.4 plus 0.4, which is 0. So what that means is that because this battery V2 is so strong and it's pushing sort of against battery V1, it sort of blocks that current. We wind up getting just one current loop with currents in IB and IC. Now that's very lucky if it's right that it worked out that way, just depending on the particular voltages and resistances that I picked. So if we go back and look at the directions, IC was in the correct direction, but IB was in the wrong direction. See, the current cannot flow through battery V2 this way because it's too strong. It's 16 volts. So it actually pushes the current the other way. We get 0.4 amps going up through R2 and then 0.4 amps going down through R3. So I don't have to change anything, though. My answers combined with my picture give me all of the information that we need. We do not want to go in and change our picture. We just want to say that IA equals 0 amps, IB equals -0.4 amps, and IC equals 0.4 amps. Hope I didn't make an algebra mistake in there somewhere. It's pretty easy to do that. And then we use, the picture to help us interpret what this minus sign means for IB. Okay, I want to do a little more practice. I'm going to make a more complicated circuit, and we're not going to try to solve this one because it's going to be too complicated. We're just going to use it for practice writing down the rules. Okay, so So we have an R1, an R2, R3, R4, R5, R6, and a V1 and a V2. So first, how many junctions do you see? I see 4. Do you see 4 junctions?
Yeah, that looks like 4.
Yeah, so let's see. There's one, there's another, there's another, there's a 4th one. So we can call these 1, 2, 3, and 4. And write down our junction rules. So that means we have to label our currents. I think it might be worth it to make this drawing a little bit bigger. Yeah, let's just make this kind of full page, and we'll do our drawings, our equations on the bottom for the junctions. So we're going to label maybe IA, IB, IC, ID, IE, and IF. So basically, between every pair of junctions, we need to label the current separately. So between, junction 3 and junction 1, moving around to the left, that's current IA. Between junction 1 and junction 2, that's IC. Between junction 1 and 4, it's IB. Between 2 and 4, it's ID. Between 2 and 3, it's IE. And between 4 and 3, it's IF. So every pair of junctions, has a new current labeling between it and any neighboring junction. So for junction 1, the current going in is IA, and the current going out is IB plus IC. For junction 2, the current going into it is IC, and going out is ID plus IE. For junction 3, going in, we have IE and IF. So that's IE plus IF. And going out, what is it? Well, we have to look all the way around and find IA up here. That's the same stuff. And for junction 4, going in is IB plus ID, and going out is IF. So those are my 4 equations coming from the junction laws. Now, junction laws are in general easier than loop laws, both to figure out the formula, but also to use because there's no resistances in there. So generally, we want to use as many of these as we can, but we cannot use all 4 because they're not independent. Then we want to do our loops. So let's just draw as many loops as we can in the picture. So you go ahead and try to draw as many loops as you can find. Take a couple of minutes to do that. And let's just label them 1 through, 15. Okay, it won't be 15, it won't be that many, but 1 through whatever. In a couple of minutes, I'll draw some loops. I guess maybe don't write numbers on the loops, because that way the numbers you write and the numbers I write might be different and it will be confusing. So don't give them numbers. So I'm getting 7 distinct loops. You guys coming up with 7 loops? So I kind of use different colors for them because I felt like it might be too crowded. So maybe we could call the loop that's just the left half of the diagram, call that one loop 1. And the loop that is sort of surrounding the word R4, so this sort of top little square, we can call that one loop 2. And the bottom square on the right, we can call that loop 3. And the square around the outside, the loop that goes all the way around the exterior, we can call that loop 4. I think those 4 are maybe the easiest ones to find. Additionally, we have another loop that would be the entire right-hand side. I did that in orange. We can call that loop 5. And then the 2, I think, kind of tricky ones are in blue. It's like a Tetris piece. Tetris. It's like an angled piece. It uses the entire left-hand side and then the top square on the right. We can call that one 6. And then in fluorescent green, it's sort of that same piece flipped upside down. So it uses the entire left-hand side and the bottom right square. And we can call that one 7. Okay, so that's a lot of loops. It's kind of confusing drawing. But let's see if we can write down all the formulas. Okay, we'll start with loop 1. So loop 1 was just the left-hand side. We should have a positive V1, and I did all of my loops going clockwise. Okay, all of them are going clockwise. So we have V1, and then a minus IC R1, and a minus IE R2 equals 0. So in both of those resistors, the loop direction I drew and the current is going, we're going with the current in our loop direction. So we get minus signs. Any questions about loop 1? Loop 2, we have a plus R1 or IC R1, and then a minus IB R3, and a minus IB R6, and then a plus ID R4. So that is, we're going against the current for R1. We're going with the current for Rs 3 and 6. And then we're going against the current again for R4. So against the current gets a plus sign, with the current gets a minus sign. For 3, we have a plus IE R2. So that's my first resistor is R2. I'm going up in my loop direction against the current. And then when I go across R4, I'm going with the current. So we have minus ID times R4. Then I cross this battery, but I'm going the wrong way. So minus V2. And then as we go across R5, we're going in the direction of the current IF. So we have a minus IF times R5. And the last sort of single loop is the outside loop. We have a V plus V1 minus IB R3 minus IB R6 minus V2 minus IF R5, and that brings us back. So we go around the outer loop, we have V1, then R1, R6, V2, and R5. And everything's negative except for the V1. Then for loop 5, I'm starting it, I guess, technically above the R2, so I'll include that kind of last. So I have a plus IC R1, because I'm going against the current as I go across R1. Then a minus IB R3, and a minus IB R6, then a minus V2, a minus IF R5, and then finally a plus IE R2. So that you might have put the IE R2 first instead of last. Okay, now the hard ones. I mean, maybe 5 is the hard one, but 6. So 6 is the one I called blue. We start with V1. And then we have a minus IB R3 and a minus IB R6. But then the blue line cuts to the left as it goes across R4. So it's going to go against the current. So we get a plus ID R4. And then we go with the current again as we go across R2. So a minus IE R2. And that's the end of that loop. Last but not least is number 7. Number 7 has, it's green. It goes first across the battery V1, and then it goes down across R1. So we have a minus IC R1 because we're going with the current. Then it follows current ID, so minus ID times R4, goes across battery V2 opposite to the way that V2 is trying to push the current, so it gets a minus sign. Then we have a minus IF R5. And that's it. We get back to the beginning. Okay. So this is a system of, let's see, 7 plus 4, 11 equations. And how many unknowns do we have? We have currents A through F, so that's six currents. So there's way more equations than we need. If I'm looking at these, I would probably prefer not to use equation 5 or even 4, 6 and 7. I'd probably stay away from all of those, and I might try to use equations 1, 2, and 3, and then 3 of my loop laws. But I might need, it may be that there's only 2 independent equations here, and I need to use 2 of those and 4 of the other ones. How many of you are thinking about electrical engineering? Anyone here thinking about electrical? Maybe Mike? Yeah, so if you're doing electrical engineering, I mean, this is bread and butter. You have a circuit much more complicated than this one, and you have to write down this series of equations. And then, you can express those equations as a matrix, and then you can do what's called a matrix inversion. And that will allow you to directly solve for all of the unknowns. So it's a pretty standard code, pretty standard routine. Virtually every language you might use has matrix inversion pretty much built into it. So the key is not, can you solve this complicated system of equations? Because the computer solves the system. The key is, can you write down the system and get all of the signs right? That's really what you should focus on. I can tell you right now, this is my #1 least favorite thing to grade when I'm grading exams out of any physics class I teach, because you could do everything right except you get one minus sign wrong somewhere. And then when you try to solve it, you're going to get it's going to go crazy in a totally different direction. And it's so hard to follow the work and see, did you just make that one mistake? Or did you then continue making other mistakes that were not related to that first mistake? It's really a nightmare to grade, which means I probably don't give you too many of these on your contest, at least not that complicated. But you need to practice it. You need to practice it. And practice makes perfect. I know I say that with a lot of stuff, but it's especially true here. So I gave you a bunch of problems that are circuits that ask you to find the currents, and or maybe once you find those currents, find the voltage between 0.1 and 0.3 or something like that. So, but you may find that you kind of feel like you're getting it before you've done all of those, and it's fine with me if once you feel like you really have mastered these rules, that you really only look at the problems that have a little something different.